This week we're going to look at several applications of derivatives. And the first one is related rates, which remember is actually number 4 in our list of chain rule consequences. But I did separate it. I think it's a little harder than the first 3, and I'd rather you get used to the first 3, particularly the second one, implicit differentiation, before moving on to related rates. So remember, with velocity and acceleration, we were actually interpreting derivatives as rates of change. Now we're not going to think of these in terms of velocities. We're going to think of them as general rates, and we'll see where the rates show up. But before we do anything with related rates, let's make one recollection. Given x squared plus y squared equals 25, remember, y in this case is not a function of x, but it is implicitly defined in terms of x. We can differentiate that equation with respect to x. And when we do that, we get 2x, because x is just x. And when we differentiate y, we treat y as an implicit function of x, as being defined implicitly by x. And because of that, we use the chain rule and get a dy dx. But we're going to look at a slightly different context. If x and y are functions of time, which we'll call t, so x in these contexts will measure a quantity, y is going to measure another quantity, and they're going to be changing as time changes. In other words, they're functions of time. Well, if they're both functions of time, then they have a bunch of t's in their function definition. Well, if that's the case, we can differentiate with respect to time. And what do we get? Well, x is a function of time, so we have to apply chain rule just like we did here. X is a function of time, so 2x, and then multiplied by dx dt, how x is changing as time is changing by the chain rule. X is a function of time. Just like here, y was kind of a function of x. We can differentiate, I assumed this equation. We're differentiating this equation with respect to time now, with respect to t. Y is also a function of time. Well, y is also a function of time. To differentiate, you have to use chain rule. And then the other side equals 0. Now these dx dt, dy dt measure how x and y are changing as time is changing. And of course, that's another way of saying they are rates. So we're going to look at specific examples of this. So first example, a 10-foot ladder is leaning against a wall. It begins to slip so that the bottom of the ladder is moving at 3 feet per second. How fast is the top of the ladder moving when the bottom is 6 feet from the wall? And with these related rates questions, I generally like to follow the same line of thought. And step 1 is going to be draw a picture. And from the picture, we're going to get an equation or possibly equations. But first, take this example and turn it into a picture. Well, what do we have? We have a 10-foot ladder leaning against a wall. Okay? We can't actually draw the ladder sliding, but we can draw a ladder leaning against the wall and then interpret that sliding. So right here, that vertical thing will be the wall, that'll be the ground, and we have a 10-foot ladder, and we're going to label that with 10. Now, also in this picture, interesting. I said we're not going to show the ladder sliding away from the wall. We actually are going to. I should have realized that when I said it. In this picture, there will be quantities which change. Which quantities change? Well, before which quantities change, those quantities which do change, we're going to use a variable to represent. And since they're changing as time is changing, these variables are going to be functions of time. So what here happens? So we have this ladder leaning against the wall. It begins to slide down. So it goes like that, slides down the wall. Well, this quantity is changing from here to here. Let's call it x. This quantity is also changing from here to here. Let's call it y. And this is going to be a right triangle. Okay, that's great. We've drawn a picture. It has quantities which change. Next, what we're going to do, you could immediately from this get an equation. In some of them, it might not be obvious which equation you want immediately. So I'm going to call step 2 something else, and then step 3 will be the equation. Step 2 is going to be translate the question. Translate the question into a language which uses rates, which uses quantities like these. Translate the question into something which uses rates and, this diagram. So what do we have here? What's this question actually asking? How fast is the top of the ladder moving? Well, how fast is the top of the ladder moving? What here measures where the top of the ladder is? There's the top of the ladder. This quantity y is telling us where the top of the ladder is. How fast is it moving? Well, that's just saying how is y changing as time is changing. In other words, find dy dt. Our goal is to find dy dt. Okay, when do we want dy dt? Well, let's see. We want when the bottom is 6 feet from the wall. Well, what measures where the bottom is? X. So we want dy dt when x equals 6. I'm going to leave a gap here. When x equals 6, what else does this question tell us? 10-foot ladder leaning against the wall? Well, that doesn't really tell us much. We already took everything we could take from that statement. It begins to slip, so the bottom is moving at 3 feet per second. The bottom is moving at 3 feet per second. Well, what does that mean? I guess I said I'm going to put a gap there. Maybe I should put that gap there. So 3 feet per second, the bottom is moving. Well, x measures where the bottom is. It's moving at 3 units of x per second. X is measured in feet. So x is changing as time is changing at a rate of 3 feet per second. Well, okay. That's great. Actually, before I fill in the other thing I was going to fill in here, I'm just going to move on to 3 and then fill it in a moment. I'm going to leave a gap about that big here. 3. Find an equation. An equation has a cube. Find an equation. Well, here we have a right triangle. And of course that satisfies Pythagorean theorem. So we have an equation relating x and y. And what did I call fourth step? Oh. And fourth step will be differentiate with respect to time. Well, x and y are changing as time is changing, so they are functions of time. Jeez. 2x because it's x squared, so by power rule we get 2x to the 1. dx dt by chain rule, x is a function of time. Y is also a function of time, so we get 2y dy dt. Derivative of 100 with respect to time is 0. 100 doesn't change as time changes. So maybe I should say differentiate with respect to time and solve. Or maybe I could say step 5, so I'm just going to leave it as it's written. So what does our question ask? Find dy dt with certain conditions. Well, right here we have a dy dt. So if we want to solve for that, subtract this, divide by 2y. But let's, before doing any of that, just make our substitution. So we want dy dt when x equals 6. You could divide everything by 2 here. When x equals 6 and dx dt equals 3. Well, with all of our substitutions, we have a dy dt, but there's also another variable in the way. Y. Do we know anything about y? Well, yes, we do. Because we have a given x value, we can use this equation to find y. In this case, y would equal 8. Why would y equal 8? Or why does y equal 8? Well, you could substitute here and then do square root of 64. You could also remember that we have a 6, 8, 10 right triangle with sides in ratio 3, 4, 5. Either way. So y equals 8. Making the substitution gives us a bunch of numbers and the quantity we want. So solve for that. What do we get? 36 plus 16 dy dt equals 0. So dy dt, subtract 13, divide by 16, you get 13 over 16 with a negative. So what's that? 18 over 8 with a negative, 9 over 4 with a negative. And units feet per second. So we get negative 9/4 feet per second. Let's make an observation about this. Let's look at these two rates. dx dt is 3, positive 3. dy dt is 9/4, negative 9/4. Why is one rate positive and the other negative? Well, what's happening in this situation? The ladder is sliding down the wall. As time changes, x is getting larger. As y changes, y is getting smaller. And that's reflected in these rates with a positive and a negative. Just like velocity, if you're walking forward, it's a positive velocity. Walking backwards, a negative velocity, assuming you define the forward direction to give you a positive velocity. In these examples, I frequently find drawing the picture and maybe translating the question is a little more important than drawing the picture. Steps 1 and 2 are really the bulk of the thinking, because once you get here, it's following a procedure. Differentiate with respect to time, and then substitute what you get into in step 2, and then solve. Let's look at another couple examples. Next, a spherical balloon is being inflated at 3 cubic feet per second. How fast is the radius of the balloon changing when the diameter is 14 inches? Now, step 1 is draw a picture. Sometimes you don't really have to draw a picture, and you could draw a sphere if you want. But I'm not going to actually draw a sphere. But we do observe that we're being asked what? How fast is the radius changing? Well, let's say it like this. Question is asking. What is the question asking? How fast is the radius changing? Well, it wants us to find how the radius is changing. Find dr dt. When? How fast is the radius changing when the diameter is 14? Our equations for a sphere are not going to be in terms of diameter, so we do have to make the observation radius is 7 when the diameter is 14. What else does it tell us? A spherical balloon is being inflated at 3 cubic feet per second. Well, that's a rate. Which rate? Well, it's telling us how the volume is changing. So we want... Stepped on the microphone. We want how the radius is changing when the radius is a certain value and the volume is changing at that rate. Well, next we need an equation relating volume and radius. Well, there's our equation relating volume and radius of a sphere. In terms of equations, if we go over an equation then it is one that could show up. I don't ask questions with like volume and area equations that we haven't gone over. So here's the volume equation. This balloon is being inflated, so volume and radius are both changing as time is changing. So we can differentiate with respect to time. On the left side, the derivative of v is 1 from the constant rule. Constant times x, the derivative with respect to x is constant. So here, constant times v, the derivative is constant, which is 1, but then you use the chain rule to get 1 times how the volume is changing as time is changing. Because remember, we're differentiating with respect to time. And what does this equal? Well, derivative of r cubed is 3r squared dr dt with respect to time. 4/3 pi goes along with that. So we get 4/3 pi times 3r squared. 4/3 and 3 in the bottom and 3 in the top cancel, and we just get 4 pi r squared dr dt. Well, now we just have to put our numbers in. Find dr dt. There it is. When this thing is 3 and r is 7. So r squared is 49. Solve for dr dt. Equals 3 over, what's 4 times 49? Well, it's 4 times 50, minus 4. You can also divide by pi. And what are our units? Probably feet and seconds. Yes. Notice these first two examples we went over, they all described a situation which was changing. But they asked about what happens at a certain fixed time that it's changing. So the first one said, a ladder is moving down a wall. What happens when the bottom is 6? This one says, a balloon is being inflated. What happens when the radius is 7? These are all going to describe a situation which changes in order to get our variables, and then it's going to ask what happens at a certain time in that change, or at a certain time that they're changing. Let's look at this next one. This next one is, I would say, definitely harder than the first two. At noon, ship A is 100 miles west of ship B. Ship A sails south at 25 miles per hour. Ship B sails north at 35 miles per hour. Find the rate at which the distance between them is increasing at 4 p.m. Well, that's a lot of information. Let's start drawing our picture up here. Ship A is 100 miles west of ship B. A and B. Okay? Not okay. I'm putting the 100 there for a reason we'll see in a moment, so it's not in the way. Excuse me. Ship A sails south at 25 miles per hour. Okay. There's a quantity which is changing. When doing calculus, I always like x, y, and z if we need a third variable, unless we're talking about a radius and a volume. So I'm going to call that x. Ship A sails south, ship B sails north. Okay. So there's another quantity which is changing. Find the rate at which the distance between them is increasing at 4 p.m. Well, ship A is down here at 4 p.m. somewhere. I mean, it's 100 down, but we'll get there. Ship B is somewhere up there at 4 p.m. So this quantity right here, that diagonal, measures the distance between ship A and B at a given time. Let's call this Z. I always cross my Z's because my 2's look like Z's. And this Z is written, parallel to the diagonal. So that quantity measured by the diagonal is going to be Z. And notice that, of course, is changing as time is changing because these ships are going north and south. Okay, great. Now we need to translate the question. And an example like this is actually why I put translate the question before find an equation. Because right here, it is certainly not obvious what the equation relating x, y, and z is. So let's translate the question. Find the rate at which the distance between them is changing. Find the rate at which the distance between them is changing. Well, z measures the distance between them. So we want dz dt is increasing at 4 p.m. We're going to need an x, a y, and a z. What is x at 4 p.m.? Well, x is changing at 25 miles per hour. Starts at noon, travels for 4 hours. You go 25 miles every 4 hours, every hour. In 4 hours, you go 100 miles. Similarly for y goes 35 miles every hour. 4 hours would be 35 times 4, which is 70 times, or plus 70. 140. What is z? Well, I'll tell you right now. It's 260, and we'll see where that comes from in a moment. But I'll tell you now that it's 260. And once we get the equation, we'll see that. But there's a little more information in this. We used these rates to figure out something. They are still rates. So dx dt equals 25, and dy dt equals 35. Well, that's great. So we still need to know where z comes from, and to do that we need an equation, which we have as part 3. How can we find an equation relating x and y? Well, it's kind of triangular. Labeling this point, not a good idea, because it would introduce another variable. That point changes as time is changing. But what else can we do? I drew my dz dt a little large. I'll just recreate this diagram over here. In your notes, you don't necessarily have to recreate this diagram if you're taking notes. And z. Well, what can we do? We can make a big triangle, like this. And now, on this big triangle, well, it's a right triangle, so the Pythagorean theorem must be satisfied. The bottom is 100 because this up here is 100. What is the other leg? Well, the other leg, remember, this distance is x, and this distance is y. So now we get our equation. 100 squared plus x plus y squared equals z squared. And we did that by adding a couple lines, I guess I should say. I should have written that at the top of the board. Well, this is on video, so if you need this diagram again, you can go back a few seconds. So we get our equation, step 3, 100 squared plus x plus y squared equals z squared. Well, now, what is z from this? Maybe I shouldn't have gotten rid of the big triangle. The big triangle is 100. This other leg was x plus y, 240. Why is the hypotenuse 260? Well, 100 and 240, that's similar to 10 and 24. Those also have a 2. So you get a 5 and a 12. With a 5 and a 12, hypotenuse is 13. So we keep that in mind. We have a 5, 12, 13 triangle. So 5 times 20, 12 times 20, 13 times 20. Which is equivalent to substituting here, but those numbers might be kind of a pain to work with. Well, okay, now we just need to differentiate with respect to time. Now the differentiating here is a little more complicated than before because of this quantity. You could multiply that out. If you did that, you'd have a tedious product rule to deal with. So I'm just going to do it like this. Differentiate with respect to time. A 100 squared doesn't change, so 0. What about this? Well, that's a quantity squared. So the derivative is 2 of that quantity to the first. But then, by chain rule, you have to multiply by the derivative of that inside quantity. Derivative of x plus y, well, you do it one piece at a time. X and y are functions of time. Derivative of x with respect to time is 1 dx dt. Derivative of y with respect to time is 1 dy dt. That's a y. I'm going to have to erase a little bit of that, I think. Well, and then on the right side, it's another, like in the first one, 2z, and then chain rule gives us a dz dt. Those lines look dark. Well, now we just have to substitute and solve. We're looking for dz dt. It's right there. I'm just going to, in the other ones, I didn't solve for the quantity and then substitute. I substituted, then solve. I'm going to solve and then substitute here. So dz dt divide by 2. And that goes away. Divide by z. I'll put it on that term. This is kind of a nice looking equation when you solve for dz dt. That's dy dt. I screwed up right in the last parenthesis. But now we substitute. X is 100. Y is 140. Z is 260. Dx dt, 25. Dy dt, 35. Well, how do we solve this? Or simplify this, I should say. Cancel a 0 from everything there. Cancel a well, maybe not even cancel 0. The top is 240. So we have 240 over 260, 24 over 26, 12 over 13. Plus 25 plus 35 is 60. 12 times 6 is 72. And 72 is not a multiple of 13, because 13 times 5 is 65. Not feet, let's write feet the third time. How about miles per hour? So in this one, we had to be a little clever in finding our equation. But once we found the correct equation, it again was differentiating and then substituting and solving. I will say for the record, this 260, I didn't just look at that and say, oh, it's 260. This is probably the 7th or 8th time I've done this example, so I know it's 260 pretty quickly. Let's look at a fourth example, which I would say is harder than each of the first three. The volume of a cube is increasing at a rate of 10 cubic inches per second. How fast is the surface area increasing when the length of an edge is 3 inches? Well, we have a cube here, and we're asked if, well, I guess I'll draw a cube. We're asked what about surface area? Well, let's label a side x. And before writing equations, we're going to, in this translation of the question, we're going to introduce some variables. How fast is the surface area increasing? Well, okay. I'm going to call surface area capital S. Find ds dt. When? Well, when the length of an edge is 3. X is 3. What else are we given? The volume is changing. So we're asking about surface area and volume at the same time. So dv dt equals 10. And there are units on all of them. Well, that's great. We're asked about surface area. Well, what's the surface area of a cube? Well, surface area is the area of the outer surface of the cube. Right here, we have an x squared on the outside. But there are 6 sides. 6, what's the word? Faces of a cube. So we have an x squared plus 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 x squared. Also known as 6x squared. Well, that's simple enough. Let's differentiate with respect to time. ds dt equals what? Well, it's 12x. S, x, and v are all changing as time is changing, so we can differentiate with respect to time. But in particular, x is changing as time is changing, so you need the chain rule. You get a 2x dx dt times 6. Well, okay, let's substitute. Equals 12 times 3 dx dt. Huh. I don't see a dx dt written anywhere here. Are we given anything about how the side length is changing? Well, no. But we are given information on how the volume is changing. And we haven't used anything with the volume. Can we use information about how the volume is changing to find how the side length is changing? Yes. Can we do it by taking a cube root, since volume is x cubed? No. But what we can do, for note-taking purposes, this space is blank for a reason. What we can do is differentiate the volume function with respect to time, and see if that helps. Well, look at that. Another dx dt. Can we solve for it? Well, dv dt is 10. And of course, dx dt and dv dt show up from chain rule. 1 dv dt, just like here, 1 ds dt, is 3x squared dx dt. So 10 equals what? 3 times x. What's x? 3. So x squared is 9. So dx dt is 10/27. Well, isn't that great? So we have 36 times 10/27. How do we do that? Well, you could do 360 divided by 27. That'd be a kind of annoying fraction to simplify. Or you could bring that 27 out and get 36 over 27 right there, and then multiply by 10. So we get 40/3 inches squared per second. Surface area, a two-dimensional quantity, 2 inches squared. Now in this one, we followed our same procedure, but we arrived at a place where we needed additional information. And we used another equation to find that additional information and then solved. Divided by 9. well, divided top and bottom by 9. Cancel the 9, I should say. And then solve. So these related rates questions, I don't think they're easy. I don't think any related rates question is easy. But definitely, if you're not just asked about a shape, definitely try drawing a picture and then just see what kinds of equations you can find. And always keep in mind which quantities are changing as time changes.